Hello everyone and welcome back in the class. So in today's class we will discuss about the Gauss law. So let's see it everyone, the Gauss law, and first of all we will see it, what is the statement of the Gauss law. So see it here everyone, here we have a statement. The law states that the total electric flux outward through a hypothetical closed surface known as Gaussian surface is equal to the net enclosed charge divided by permittivity of the free space. Correct. And if we will write this Gauss law mathematically, so how it can be written as everyone, phi equal to close integration. This phi is representing here flux everyone. This is representing close integration. This E net is the net electric field. dA is area of the small element. Correct. And in between this E net and dA we have here dot product also. And we know that if we are doing dot product between E and A, then we are getting flux. Correct. And equal to q in by epsilon naught, where q in is what? It is the charge present inside the closed surface divided by epsilon naught. So according to definition of this Gauss law, this thing we are getting everyone. Like this we can write down this Gauss law mathematically, and this is important. Right? Now let's see it everyone. Let's suppose here we have one arbitrary shaped closed surface. Correct? So this is the arbitrary shaped closed surface. This is Gaussian surface, and let's suppose plus q1 minus q2 charge is present inside this Gaussian surface, and plus q3 is present outside the Gaussian surface. And let's suppose at this p point we want an electric field. Correct? So now we need to apply here Gauss law, and when we are applying the Gauss law, correct, so here we have required q in. So for this case, when I will write q in, so q1 is what? It is everyone q1 minus q2. Correct? Here we are considering only enclosed charge. Correct? Only charge present inside this closed surface. This charge only we are taking, not outer side charge. So q3 we will not take because it is present outside the surface. So q in value is what? For this example everyone, it is q1 minus q2. Alright. But what about the electric field at this p point? So when we will find the electric field, or when we will write the electric field at this p point, so here we are getting net electric field. You can see it here. Correct. In this formula here, this is the net electric field everyone. This is net electric field. Correct. Means electric field due to the inner charge as well as outer charge also. So at this p point, when we will get electric field due to this Gauss law, then here this E we are getting net everyone. It is present due to the inner charge as well as outer charge also. No need to think like that we are not considering this q3 charge, so due to this we are not getting electric field at this p point. Effect of this q3 is also present here, but when we are applying the Gauss law, then only we are taking inner charge only. So keep this thing in your mind everyone, how we can apply the Gauss law. Correct? What is E net here? Correct? What is the dA here? What is the q in here? How we can take q in? So I hope right now this all things are clear. So note down everyone. Let's see next point everyone. So what is the next point? If we are considering closed surface, so we should keep some point in our mind. If we are considering closed surface, so this closed surface such a way that so electric field should be perpendicular and parallel to this closed surface. So if electric field is parallel and perpendicular to the surface, then what will happen here everyone? Then calculation is becoming easy here. This is the benefit of this. If we are considering random shape, then what is the problem here? Then calculation is becoming difficult here. So if you want to make easier calculation, so electric field should be parallel and perpendicular to the closed surface, then your calculation is become easy. So see it here, two cases everyone, then you will get it. Why electric field should be parallel and perpendicular to the surface. So let's suppose here we have plus q charge, and due to this plus q charge we want electric field. So in the case 1 we are considering here q, correct? So and we want electric field at this p point. All right. So now next what we will do it, we will apply here Gauss law, which is E dot ds equal to q in by epsilon naught. So close integration E dot ds equal to q in by epsilon. This is Gauss law. All right, so here charge present inside the closed surface is what is the q. So q in value is q here. Now here we have electric field and ds. Ds is the area of the small element. Let's suppose a small element, if I am considering here, I'm taking this is a small element. So what is the direction of electric field for this small element? This is the direction of electric field. And what is the direction of area vector? It is perpendicular to the surface. So ds and electric field we have in this direction. And this angle is theta1, everyone. All right. Now consider one element here. So electric field is this is the direction of electric field, everyone. And now this is the ds perpendicular to the surface. Correct. So this angle is, let's suppose, theta2. If you will take another element here, so direction of electric field is this, everyone, and area vector is perpendicular to the surface. So here electric field different. Let's suppose it is E1, this is E2, this is E3, because distance between the charge and the element is different. That's why it is happening. And you can see it here, angle is also different here, and this is ds. So we can see it here, electric field for all the element is different. So electric field is not constant here, everyone. It is variable. Electric field is variable. All right. After removing the dot, we will get cos theta. So if I will remove this dot product, then we have EDS cos theta. Correct. This thing we have. So what will happen here? See it. Cos theta, here theta is varying, everyone. So cos theta is variable and E is also variable. So here we have two variables. So easily we can't do it here calculation. So what we have to do it, we need to find out first of all angle between electric field and area vector for all the elements. Correct. We need to find out this theta1, theta2, theta3 value. We need to calculate separately here electric field also. Then we will do it calculation here. So this calculation is becoming very difficult, because here we have n number of elements, and for each element if I will do it calculation, so it will take long time. Correct. A lot of time it will take. So that's why if we are considering random shape, random closed surface, so it is difficult for us. Now in the second case, I'm considering spherical surface. Now what is the benefit of this? See, if we will look at electric field from this closed surface, so we can see it here, electric field is perpendicular to the surface. If I will take element here, then what is happening here? Electric field is perpendicular to the surface, correct? And let's suppose here electric field is E1. All right. And this distance is what, everyone? It is R. So E value is what? E value is here KQ by R square. If I will consider one element here, then what will happen? Then again this distance is R, everyone. Correct. This distance is R here. So here again electric field is E, everyone, because R is same, distance is same, charge is same, so definitely magnitude of electric field is same. So now E1 and E2 is same, everyone. Correct. So E1 is equal to E2, and this will happen for all the element. What about the theta here, everyone? Theta is the angle between the surface. This is the surface, this is a small element, and if you want direction of area vector, so draw one perpendicular. So here I am drawing perpendicular to the ds. So theta is here what? It is the 0. For this element also we will find. So theta is what, everyone? It is 0. Correct. So for all the elements, theta is 0 here, everyone. Means theta is constant here. Electric field is constant. Theta is constant here. Correct. So now if E and theta is constant, so both are constant here. So easily we can do it calculation. E dot ds Let's see it, everyone. E dot ds, remove dot product sign, so we have eds cos theta. All right, and q in value is q divided by epsilon naught. Electric field is constant and theta is constant here, and theta value is 0 also, so cos 0 value is 1. Electric field is constant, so put outside the integration. Now we have only ds, and this is cos 0. Cos 0 is 1. Correct. Now I'm taking next space. Space is less. So cos 0 is 1. So now we have E ds equal to q by epsilon naught. The ds is what? It is the area of the small element, everyone. And on this surface we have n number of elements, and if we will add this all the small element present on this sphere, then this integration should be equal to surface area of this sphere, everyone. And what is the surface area of the sphere? It is 4 pi r square. So here we will write E, and ds, close integration ds can be written as what? It is 4 pi r square, because if we are adding small element present on this sphere, correct, so it should be equal to the surface area of the sphere. I think this thing is clear to everyone. If we are adding all small element present on the surface, so it should be equal to what? It should be equal to surface area of the sphere. So it is 4 pi r square equal to q by epsilon naught. All right, now the next thing is what, everyone? E equal to q by 4 pi r square epsilon naught. All right, now 4 pi epsilon naught value, 1 by 4 pi epsilon naught value is what? It is the k. So E equal to what? It is k q by r square. All right, so we got it here. Electric field due to this q charge at the r distance is what? It is a kq by r square, everyone. This thing we got it. All right, so keep this point in your mind, everyone. If you want to make the easy calculation, so when you are considering closed surface, the electric field should be parallel and perpendicular through the surface, everyone. If it is parallel and perpendicular to the surface, then your calculation is becoming easy. Correct? If you are considering any random shape, then calculation is becoming very difficult. So this is the problem here. So that's why when we are considering electric field due to the wire, everyone, then we are considering cylindrical closed surface. All right, we are not considering here spherical. All right, and when we are considering electric field due to the sheet, then again we have cylindrical closed surface. So because if we are considering this type of surface, then our calculation is becoming easy. That's why. So I hope this thing is clear, everyone, and it is important for us also. So keep in your mind this thing. Let's say this question, everyone. A sphere encloses an electric dipole with charges plus minus 3 into 10 raised to minus 6 coulomb. What is the total electric flux across this sphere? So this is the question. We want electric flux across this sphere, everyone. So it is very easy question, very basic question. So here we have spherical closed surface, and inside this we have one electric dipole, everyone. All right, plus q and minus q. So what is the total electric flux across the surface? So this thing we want, flux we want. So according to Gauss law, we know that closed integration E dot ds equal to q in by epsilon naught. This thing we know, everyone. And this closed integration E dot ds is equal to flux. All right, flux passing from the closed surface. Now when we are writing flux, everyone, so it is equal to q in by epsilon naught according to Gauss law. Q in is what? Charge enclosed inside the closed surface. And if you will look here, charge enclosed in the closed surface is what? It is 0. Plus q minus q, if you will do it, then it is 0, everyone. So it is 0 by epsilon naught. So what is the flux here? Flux is 0. All right, so flux is 0 here, everyone. So the correct answer is option C. So very easy question, correct? Just apply here Gauss law and you will get your answer. Now let's see next question, everyone. Consider the following three cone and calculate the flux through this due to the charges placed as shown. So here we have three cases and we want flux passing from this cone, all this in three cases, correct? So one by one we will see it, everyone. So let's see case number one. So here we want flux passing from this cone. So we will apply here Gauss law. So flux passing from this cone can be written as phi equal to q in by epsilon naught. All right. Qn is what? It is the charge present inside the closed surface. So we can see it here. Right now charge is present here. So half charge is present inside the closed surface and half charge is present outside. So half charge is present inside and half charge is outside, everyone. So Qn value is what? It is q by 2. So it is q by 2, everyone. So q in value is what? It is q by 2. So phi 1 flux in this first case can be written as q by 2 epsilon naught. The answer. Now see it, second case, everyone. In the second case, what is happening? The charge is present inside this closed surface. So here phi 2 can be written as q in by epsilon naught. So q in is what? Q divided by epsilon. So second case, phi 2 is what? Q by epsilon naught. Now look at third case. In the case happening. Now the charge is present outside the cone. So here phi 3 can be written as. Now charge present inside the closed surface is what? It is 0. So phi 3 equal to what? It is 0 by epsilon naught. So phi 3 value is what? 0. So in this case, flux passing from the closed surface is what? Is q by 2 epsilon naught. In the second case, it is q by epsilon naught. And in the third case, it is phi 3 equal to 0. So it is 0, everyone. So note down this thing. Let's see it. Next question, everyone. A hollow cylinder has charge q inside it along its axis at O as shown. If phi is the electric flux associated with the curved surface B, then what will be the flux linked with the plane surface A? So here we want flux linked with plane surface A, everyone. This is the question. So let's see how we can do this question, everyone. Here we want flux linked with the A. How much flux is passing from this part? This thing we want phi A value, correct? So let's see how we can do this question, everyone. Here first of all we will apply Gauss law. So according to Gauss law, net flux passing from any closed surface is equal to charge enclosed by that closed surface, which is q here, divided by epsilon naught. All right, this is the net flux. Now this net flux is passing from this A part, everyone, and from the C, and it is passing from the curve also, correct? So if we will add this phi A, phi C and phi B, then we will get the net flux. So it can be written as phi A plus phi B plus phi C, correct? Here if you will look, this charge is present in the center, so flux passing from the A and the flux passing from the C is same, means phi A equal to phi C. Phi A equal to phi C, everyone. All right. So flux passing from the A and the flux passing from the C is equal here. And what we want here, we want flux passing from the A. So now the next thing is what? Q net value is q by epsilon naught. All right. And we know that phi A and phi C is same, so it can be written as 2 phi A. Phi A and phi C is same, so it can be written as 2 phi A plus phi B. And what is the value of phi B? It is phi, everyone. In the question, if phi is the electric flux associated with the curved surface B, means phi B we have here. So phi B is equal to what? It is phi. So we are putting this value here. So 2 phi A plus phi, and this is q by epsilon naught. So now what we want here phi A. So 2 phi A equal to Q by epsilon naught minus phi. So phi A value is what? It is 1 by 2 Q by epsilon naught minus phi. This is the phi A value. So flux linked with the A surface is how much, everyone? It is 1 by 2 Q by epsilon naught minus phi. If we will check here, then which options we are getting? We are getting here option number A. So A is the correct answer. So I hope this thing is clear how we can do it this question. Note down, everyone. Let's see next question, everyone. Find out electric flux passing through the surface. So this is the question, everyone. So here we have one picture. You can see it here. This is the surface, everyone. And we want flux passing from the surface. And the side length of the surface is what is the A, and charge is present at A by 2 height from the center of the surface. All right. So we want flux passing from the surface, and charge is present at A by 2 height from the center of the surface, everyone. So how we can do it this question? Think it, everyone. If I will imagine here one cube like this, so what will happen? So if you will imagine here one cube, everyone, so now this charge is present in the center of the cube. All right. So if I will write total flux passing from this cube, it is what? It is Q by epsilon naught according to Gauss law. But here we want flux passing from only one surface. All right. We want flux pass from only through the one surface. So what is happening here? Charge is present in the center of the cube, and from the one surface we want. All right. So the flux passing from the one surface can be written as what, everyone? Total flux is Q by epsilon naught. So flux passing from any one surface can be written as what? It is Q by 6 epsilon naught. So this is the answer, everyone. So this flux is passing from this surface. Q by 6 epsilon naught is passing from this surface. Q by 6 epsilon naught is passing from this. So from every surface, Q by 6 epsilon naught flux is passing because charge is present in the center. All right. So 5 by 6, 5 by 6, 5 by 6, 5 by 6, 5 by 6. If we will add this all, then we will get net flux, which is equal to Q by epsilon naught. So I hope this question is clear how we can do it and how we can imagine, correct? Note down, everyone. Let's see next question, everyone. Find out the electric flux passing through the surface. So what is happening in this question, everyone? We have one surface, and on the surface Q charge is present, correct? So like we have this surface, and on the surface Q charge is present, and we want how much flux is passing from the surface. All right. So here we want flux passing from the surface. So first of all, if you will imagine here field lines, everyone, this is the electric field lines. So this is the field lines, correct? And if you will think it, everyone, so here only half line is passing from the surface, and half line is passing above from the surface. So only half field line is passing from the surface, and half field line is going above from the surface. All right, this thing is happening. So if I will write here total flux due to this charge, so it is Q by epsilon naught from the Gauss law, and here we want flux passing from the surface. So we can see it here, only half field line is passing from the surface. That's why the flux passing from the surface can be written as Q by 2 epsilon naught. This is the answer. So Q by 2 epsilon naught is the answer, everyone. Note down. Now we will discuss about the application of the Gauss law, everyone. So let's see it, application. So first of all, what we will do it, we will analyze these three cases, everyone. So one by one we will analyze, and we will find electric field inside and outside. So let's see it, first case, everyone. In the first case, what is happening? Here we have solid conducting sphere. So here we have solid conducting sphere. So see first one, everyone. Here we have solid conductor, and what we are doing here, we are giving some charge. We are putting some charge on this conductor. So between these charges, repulsive force will act, and due to this repulsive force, this charge will distribute on the surface, everyone. We know that in the conductor charge can move, that's why they are moving and it is distributing on the surface, correct? And radius of the conductor is what? It is a capital R. So this is the case number 1. All right. So here whole charge is present on the surface. If we will put inside also, between the charges force is acting and it is distributing on the surface. Now let's see second case, everyone. Case number 2, hollow conducting. So now in the second case we have hollow conductor. So here we have now hollow conductor, everyone. So what we are doing, we are putting some charge on this hollow conductor. So between the charges, repulsive force will act and it will distribute on the surface. And the radius is what? It is capital R, everyone. So in the second case, we have hollow conductor and we are giving some charge on this hollow conductor. So it will distribute on the surface, correct? In the first case, we are giving Q charge. In the second case also, we are giving total Q charge. Now see third case, everyone. In the third case, we have hollow non-conducting sphere. So now again we have hollow, but it is non-conductor. So the case number 3, and now we have hollow non-conducting. So what we are doing here, we are putting some charge, but right now it is hollow conducting. So here we have to distribute, correct? From yourself, you have to distribute. So because on the non-conductor charge cannot move, correct? So here we have to do work. We will distribute charge on the surface uniformly. This thing we have to do it. So now we can see it here on these 3 cases. Total charge is Q, radius is R, and whole charge is present only on the surface, not inside, correct? So if I will write charge density in this all 3 cases, so charge density can be written as sigma. Why we are using here sigma? Because here charge is only present on surface. Here charge is the function of area. That's why we are using sigma here. All right, so we will write here sigma charge divided by surface area. And what is the surface area? It is 4 pi r square. So we will write here Q by 4 pi r square. This is the surface charge density, Q by 4 pi r square. All right, so note down this, everyone, and then we will apply here the Gauss law and we will find electric field inside and outside. And for this all 3 cases, we will do it only one derivation. Result is same for this all 3 cases, because in this all 3 cases charge is only function of the surface. That's why result is same for this all 3 cases. All right, so note down, everyone, first of all this, then we will apply Gauss law. Note down. So let's see it, everyone. Now we are taking one conductor, and here we know that in this all 3 cases charge is the function of surface only, correct? Charge is the function of area, so it is only present on the surface. So here we want electric field inside and outside this conductor. So here charge is present on the surface, and radius is r here, everyone, and surface charge density is sigma. All right, so now the next thing is what? First we are taking P point inside this conductor and we want electric field at this P point. So here First of all, we are assuming, because in surface here, correct? Now R is less than to capital R, the case number 1. R is less than to the capital R. And if we will apply the Gauss law, so it is closed integration E dot ds equal to Q in by epsilon naught. And what is the Q in value? See it. Right now, whole charge is present only on the surface, correct? Inside this closed surface, charge is not present, so it is 0. So Q in is what? It is 0, everyone. So after simplification, we want here electric field, correct? So E equal to what we are getting? It is 0. So in this all three cases, electric field is 0, everyone. In the solid conducting sphere, in the hollow conducting sphere, and hollow non-conducting sphere. In this all three cases, electric field inside is 0, everyone. Now, this is a case number 1, everyone. In the case number 1, we are finding inside the conductor, that's why small r is less than to the capital R, where capital R is representing radius of the conductor and small r is what? It is the distance between the P point and the center of this conductor. Alright, and you can see it here, R is less than to the capital R. Now let's see it second case, everyone. Case number 2. And in the case number 2, what we will do it? We will find outside, correct? So here R is greater than to capital R. The small r is greater than to the capital R. Alright, so here once again we have same conductor, total charge is Q, and charge is present only on the surface. And this is the P point, everyone. At this P point we want. So this is closed surface, everyone. Alright, and now this distance is how much? This is a small r. So let's see it again. We will use here. What is the value of Q in? Q in is Q, everyone. And here dot sheet. If you will look any element present on the surface, so let's suppose I am taking here this element which is present on the surface. So direction of electric field at this point, like this direction of electric field, everyone, and direction of area vector perpendicular to the surface. This thing we know that. So you can see it here, E and ds both are parallel, and this thing will happen for all the elements, everyone. If I will take element here also, same thing we will get. Here I am taking this is ds, and electric field is radially outward direction. So here also theta is 0. So here E and ds is parallel, everyone. So that's why theta is what? It is 0 for the all elements. All right. So here dot product we have. That's why first of all we will resolve this. We will remove this dot product sign. So what we will get? E ds cos theta. EDS cos theta. Now theta is what? It is 0, everyone. Cos 0 is 1. And think it about the electric field, everyone. Now this closed surface is symmetric, everyone. Alright. So it is symmetric. So R is symmetric here for all the elements. That's why electric field is constant. So electric field is constant here, everyone. So what we can do it, put this E outside the integration ds q by epsilon naught. So close integration ds, if I will add this all small element, all right, so it should be equal to what? It is equal to the surface area, correct? So it is E 4 pi r square, correct? So close integration ds should be equal to 4 pi r square, because if you will add this all small element, so it should be equal to the surface area of this sphere. All right, now we have E equal to q by 4 pi r square epsilon naught. This thing we are getting. Now the next thing is what, everyone? We know that 1 upon 4 pi epsilon naught is what? Is the k. So can I write E equal to k, and this is Coulomb constant, everyone, and 1 upon 4 pi epsilon naught is what? It is k, everyone. So we are replacing with the k, so that's why we have kq, and here we have r square. So electric field is what? It is kq by r square. All right, so now the next thing is what here? Draw electric field versus distance graph. See, so now we are plotting here electric field versus distance graph. So look at what type of graph we have. So electric field inside the sphere, what we got it? It is 0, and outside it is kq by r square. Means we can say that E is inversely proportional to r square. Means outside we have hyperbolic relation and inside it is 0. So the graph should look like this, everyone. Should be like this. This type of graph we will get. All right. So inside the conductor it is 0 and outside it is hyperbolically decreasing. All right. So this thing we will get, and this graph is valid for this all three cases, everyone. Keep this thing in your mind, because in this all three cases charge is only present on the surface. Solid non-conducting sphere. So now we will find electric field inside and outside solid non-conducting sphere. So here we have one non-conductor, everyone. And on the non-conductor we know that charge cannot move, so that's why we have to distribute uniformly. All right, so here charge density is what? It is the rho n. And now the next thing is what? The radius of the conductor, which is capital R. Correct. Radius of this non-conductor is what? Is the capital R. And let's suppose at this P point we want electric field. And the distance between the center and the P point is what? It is the small r. All right. So here R is less than to the capital R, and this is the case number 1. Now the next thing is what everyone we want here electric field inside this non-conductor, correct? So first of all we will apply here Gauss law, close integration E dot ds q in by epsilon. All right. So if you will look angle between electric field and ds vector, ds is what? It is the area of the small element. All right. So let's suppose I am taking element here. At this point I am taking one small element. So this is the direction of electric field, and ds vector is perpendicular to the surface. So we can see it here, ds as well as electric field both are parallel to each other. So E is parallel to ds, everyone. That's why theta is what? It is 0. And it is valid for all the cases, all the elements, correct? If we will take any element, so electric field and ds vector both are parallel. So theta is 0 for all the elements. So now remove this dot product sign. So if we will remove this dot product, everyone, so we will get EDS cos theta equal to Q in by epsilon naught. Now theta is 0 here, cos 0 is 1, electric field is constant because this Gaussian surface is symmetric, everyone. So we will put here E outside the integration because it is constant. So now we have E close integration ds, and cos 0 is 1, we know this thing. So now we have only ds inside the integration, and in the right side we have q in. Q in is what? Is a charge enclosed inside this closed surface. So Q in value can be written as what, everyone? It is charge density into volume of the closed surface, which is 4 by 3 pi rq, correct? So Q in is what? It is rho 4 by 3 pi rq. So we will write this value here, 4 by 3 pi rq divided by epsilon naught. So now what will happen here? Do it close integration of ds. So here we will add a small element present on the surface. So if we will add this all the small element present on the surface, so it should be equal to the surface area of this closed surface, so which is 4 pi r square. Surface area of the sphere is what? It is the 4 pi r square. So we will write here E 4 pi r square equal to rho 4 by 3 pi r cube epsilon naught. Now the next thing is what, everyone? Here 4 pi will get cancelled out. This and this will get cancelled out, everyone. Then finally what we have here after the simplification, so E equal to, we are getting here rho r by 3 epsilon naught. This thing we are getting. Now if we will look at here, direction of electric field and position vector in the same direction. Like if we will look this point P, everyone, so this is the direction of position vector. In the same direction, electric field is present at this P point, and it is valid for all the points. If we will see point here also, if I will take one point here, so at this point, this is the direction of position vector, okay, and the electric field is also in the same direction. And if you want to draw the position vector, then what we have to do it, correct? Tail we will put at the center of the sphere, and P point, and the head of the vector we will put at the P point. All right, this thing we will do it because distance of this P dash point we are measuring from the center. That's why tail is present at the center, everyone. All right, because we are doing measurement from the center. That's why tail we will put at the center, and we are measuring P dash point distance from the center. That's why head is present here. So I think this thing is clear to everyone. How we are drawing here position vector. So here we are getting equal to rho r by 3 epsilon naught. Now rho 3 epsilon, charge density is constant here, correct? Epsilon naught is constant, 3 is constant. So we can say that electric field is directly proportional to r. Means between electric field and position vector we have linear relation. Electric field is increasing linearly here. from center to the surface. So this thing we are getting from center to surface, electric field is increasing linearly. Note down everyone. Let's see next case everyone. So now we will find electric field outside the non-conductor. So here we have this non-conductor everyone. And at this P point we want electric field. This is the center of the non-conductor. And distance from here to here is how much? It is a small r. The radius is capital R everyone. Charge density is rho here and total charge is Q. Charge density is rho and the total charge present on this sphere is what is the Q everyone. Okay. Now we are considering here one Gaussian surface. Okay. So this is Gaussian surface everyone. And here R is less than to the capital R. This is the case. So we are using here Gauss law, close integration E dot ds equal to Q in by epsilon naught. All right. Now remove this dot product sign. So if we will remove the dot product sign, so we will get cos theta. Then we have ED as cos theta equal to Q in by epsilon naught. Now theta is what? It is 0 everyone. Theta is 0 because electric field and ds vector both are parallel. That's why. Because if you will look this P point everyone, here I will consider one small element, correct, on this surface. So area vector is perpendicular to the surface and this direction of electric field which is present in the direction of position vector. So electric field and ds both are parallel. That's why theta is 0 and it is applicable for all the elements present on the surface. So for all the element theta is 0, so it is constant and it is 1 also because cos 0 is what everyone? Cos 0 value is 1. This thing we know. And what about the E? E is constant here because this closed surface is symmetric. That's why E is constant. So put outside the closed integration according to the rule. Now we have only ds inside this closed surface. Alright. Total charge is how much inside this closed surface? It is Q. So Q in is equal to Q everyone. And closed integration ds is what? It is 4 pi r square. Surface area of the sphere. If I will add all this small element present on the surface, so definitely it is equal to the surface area of the sphere, which is 4 pi r square. Now the next thing is what? E equal to we have Q by 4 pi r square epsilon naught. And we know that 1 upon 4 pi epsilon naught is what? Is the K. So what we are getting here? E equal to KQ by r square. So E is inversely proportional to r square here. So between E and r we have hyperbolic relation. So between E and R we have hyperbolic relation and here we have linear relation everyone inside the non-conductor and outside we have hyperbolic. Now we want to plot here graph everyone. So let's see what type of graph we will get. So let's say graph everyone. Okay, see it electric field versus position graph. E versus R graph. We are plotting here. So if we will look here everyone, initially what is happening from center to surface, electric field is increasing linearly. If we will look here, we have linear relation between E and R. And outside the sphere what is happening? It is decreasing hyperbolically. So graph should be look like this. from center to surface, linearly it is increasing, then hyperbolically it is decrease. Correct? So this is graph, everyone. So note down, everyone. Let's see next topic, everyone. Electric field in cavity in non-conductor. So here we have one non-conductor, everyone, and inside this non-conductor we have one cavity. You can see it in this picture, and we want an electric field inside this cavity. So as is present uniformly on this non-conductor, and charge density is rho, everyone. And let's suppose this is center of this non-conductor. All right, and this is the center of the cavity. This is center of the cavity. So it's O, and this is O dash, everyone. Now distance between O and O dash is how much? We will see it. The distance we are taking A here. So distance between O and O dash is what? It is A, everyone, and we want electric field at this P point. At this P point we want electric field. All right. So distance between O dash and P is X, everyone. So this is the vector X. And distance between O and P is how much? It is the Y, everyone. The distance is Y. All right. Now the next thing is we want electric field at this P point. So what I will do it here. First of all, I am considering in this whole non-conductor we have only positive charge. And due to this non-conductor, we will find electric field at this P point first of all. Correct? So first of all, I am considering in whole conductor or whole non-conductor we have only positive charge. So E1 can be written as rho, and distance between P and O point is what? Is the Y, everyone. We are writing electric field at this P point. Correct? So it is rho Y divided by 3 epsilon. All right. Now in the second case, what I will do it here, I will consider inside the cavity charge density is negative. Correct? So first of all, I am considering in whole non-conductor we have positive charge, inside the cavity then we have negative charge. Correct? And then we will add, then we will get net effect. All right. So now we will write electric field due to this cavity at the P point, and at the in the cavity we are considering negative charge density. So it is what? It is E2 equal to minus O X by 3 epsilon naught, everyone. This thing we will get. This is E1 and this is E2. Now we will write here net electric field. So what is the net electric field, everyone? It is E1 minus E2. Put here E1 value. So E1 is what? It is rho Y by 3 epsilon naught. And it is what? It is rho X by 3 epsilon naught. Now we will put rho by 3 epsilon naught outside. Now we have Y minus S. This we have. So this thing we are getting, and this is net electric field. Now I can do it one more thing. If I will find relation between vector A, vector X, and vector Y from the triangle of addition. So what we will get, everyone? If I will use the triangle of addition, so A plus X equal to Y, and look at value Y minus X. So vector A is equal to what is y minus x. Correct. Now put this value y minus x in this bracket. So we will get here net electric field equal to rho A by 3 epsilon naught. This thing we will get. This is the net electric field, everyone. So rho A by 3 epsilon. This thing we are getting. And relation between A, X and Y we are getting from the triangle law of addition. Now the next thing is what? Electric field we got it is rho A by 3 epsilon naught. So if we will analyze this result, everyone, so what we will find here, electric field inside this cavity is uniform, everyone, because A is constant here, rho is constant, 3 is constant, epsilon naught is constant. Correct? So at every point we will get same electric field. And net electric field and vector A is same, everyone. Net electric field is present in the direction of vector A. So electric field is constant, correct? Or we can say that it is uniform and it is unidirectional also. Every point in the cavity, electric field in same direction, everyone, in the direction of the A. So it is uniform and it is unidirectional in this cavity. Correct? Because net electric field is present along the A direction. Alright, and it is independent from the P. It's not depending on the Y. So that's why it is uniform and it is unidirectional. A is constant here. Alright. So write down this both points, everyone. Inside cavity, electric field is uniform and unidirectional. If the cavity is present at the center of the sphere, the electric field is zero. Now, what is the sense of the second point? If the cavity is present in the center, then what will happen? See, we know that inside the cavity, net electric field is what? It is a rho A by 3 epsilon naught. So when the cavity is present in the center, so what will happen? The distance between the P point and the center is what? It is zero. So it is zero. So that's why net electric field is what? Net electric field is zero. So zero net electric field we will get. So if you will put cavity on the center, then the net electric field is zero. Note down, everyone. Let's see next, everyone. Electric field due to an infinitely long uniformly charged wire using the Gauss law. So here we have infinite long wire and we want electric field into this wire, everyone. So let's see what we can do it here. Let's suppose at this P point we want electric field, correct? So first of all we need to consider here closed surface. So we are considering here one closed Gaussian surface. All right. And this P point is present on this closed Gaussian surface, everyone. And let's suppose charge density is lambda here. And positive charge is present on the wire. And now the next thing is what? Distance between the P point and the wire is what? Perpendicular distance is what? It is small r, everyone. All right. Now the next thing is what? Length of the cylinder. So small l. So apply here Gauss law. So according to Gauss law, closed integration E dot ds equal to q in by epsilon naught, correct? Q in is what, everyone? It is the charge present inside this Gaussian surface. So length of the cylinder is L, charge density is lambda. So Q in can be written as lambda into L, correct? So Q in value is lambda L, everyone. Now the next thing is what? Here E and DS both are parallel. So angle between electric field and ds vector is 0, everyone, because both are parallel. So theta is what? It is 0. So here theta is 0. So if you will remove the dot product sign, then what we will get, everyone? E ds cos theta, and theta value is 0, so cos 0 is 1. Electric field is constant. Put outside the closed surface, put outside the integration, and cos 0 is 1. So now we have only ds inside the integration, and see it here, this ds element is present on this closed surface. All right, so if you will add this all the small component, everyone, then it is equal to the surface area of the cylinder. All right, and length of the cylinder is L, radius is R. So surface area of the cylinder is equal to 2 pi RL. Now L is cancelling here, so we have E equal to lambda by 2 pi R epsilon naught. This thing we have. Now the next thing is what? We can see it here, E and R both are present in inverse relation. So we can say that E is inversely proportional to R. Means between E and R we have hyperbolic relation. Now see what type of diagram we will get here. If we will plot a graph, so what type of graph we will get? Let's see it, everyone. Now we are plotting here graph between E and R. So here we have hyperbolic relation. So this type of graph we will get. E versus R graph. Note down, everyone. So electric field due to the wire we have E equal to lambda by 2 pi R epsilon naught, and if we will plot graph between the electric field and the position vector, so we have hyperbolic graph. Note down. Let's see next topic, everyone. Electric field due to infinite long uniformly charged solid conducting and hollow conducting thick wire using the Gauss law. So here we have two cases, everyone: solid conducting and hollow conducting thick wire. And for both the cases, we will get same results. Why? Because charge is only present on the surface. If it is conductor, everyone, so let's suppose I am giving charge in the center, but it is the conductor. So on the conductor, charge can move. Then what will happen? Charge will distribute on the surface. Correct? So if we have hollow wire or we have solid conductor, in the both cases, charge is only present on the surface. Correct? So charge is only present on the surface. So here charge is the function of area, everyone. Function of surface here. So here charge density we will represent with the sigma. Sigma is the charge density. And the radius is capital R, everyone. And at P point we want electric field, correct? So how we can find out electric field at the P point? So we need to consider here Gaussian surface. So here we will assume closed surface, everyone. That's it. And this distance is what? It is a small r. Correct? So in the case one, R is less than to the capital R, correct? Because point is present inside the conductor everyone, that's why small r is less than to the capital R. Capital R is what is the radius of the cylinder. Now the next thing is what? Apply here Gauss law. We are looking for the electric field, so we are applying here E dot ds equal to q in by epsilon naught. What about the q in everyone? Here whole charge is present on the surface everyone. Inside the closed surface, charge is 0. So q in is 0 everyone. If q in is 0, then definitely E is 0. So electric field inside the wire or inside the cylinder is what it is the 0 everyone, because whole charge is present only on the surface. That's why it is happening. So write down everyone, then we will see next case, case number 2. Let's see it, case number 2 everyone. So here in this case we will find electric field outside the conductor. So here we have P point and this P point is present outside the conductor. All right, and this is closed surface everyone. It is the Gaussian surface. And this is the direction of electric field due to this conductor. And at P point we want value of electric field, and distance between this axis and this P point is what everyone? It is a small r, and the radius of this conductor is capital R. All right. Now the charge density is what? It is sigma everyone. So in this case R is greater than to capital R. So write down here close integration E dot ds q in by epsilon naught. So what is the value of q in everyone? Q in is the charge present inside this closed surface, correct? So sigma into 2 pi RL. And here we are finding charge present on the cylinder everyone. So surface area of the cylinder is what is 2 pi RL. So here we will write capital R. And length of this closed surface is, let's suppose it is L. So it is 2 pi RL divided by epsilon naught. Here electric field and ds both are parallel, so correct, this both are parallel everyone. So theta again in this case we have 0, cos 0 is 1. Electric field is constant because this closed surface is symmetric, that's why. So what we will write here, E we are putting outside the integration, and here we have already ds. Now do it close integration of ds. So we are adding a small element present on the surface. So if we will add this all, then it is equal to the surface area of this cylinder everyone, correct? So here flux we are getting only from the curved part only everyone, only from the curved path. All right, let's see it here. Let's suppose this is cylinder everyone. So field line is perpendicular to the curved path. And if we will look at this circular path in the lower side and the upper side, so here field line is parallel. So from here flux is not passing. That's why we are not talking about this circular path everyone. Here we are only considering curved path because all the field line is passing through this curved path only. That's why. And the surface area of the curved path is what? It is 2 pi RL. So here we will write E 2 pi RL. So I think right now this thing is clear why we are taking surface area of the curved path only, because field line is only crossing from the curved path. Now the next thing is what? 2 pi will get cancelled out, LL will get cancelled out. So we have electric field is equal to sigma R by 2 epsilon naught. 2R, 2 is cancelled, correct? So we have only R epsilon naught. This thing we are getting. So here electric field is inversely proportional to R. Okay, so electric field is inversely proportional to R, this relation we are getting. So inside the conductor, if we will look, electric field is 0, and outside we have hyperbolic relation. So now let's see it graph, everyone. Electric field versus distance graph. So look at electric field versus distance graph. So inside the conductor we have 0 electric field, and outside it is decreasing hyperbolically. So this type of graph we will get. Correct? So note down, everyone. Let's see next case, everyone. Electric field due to an infinite long uniformly charged solid non-conducting thick wire using Gauss law. So here in this case we have solid non-conducting thick wire, everyone, and we want electric field inside and outside this non-conducting thick wire. So we are taking here one non-conductor and we are distributing charge uniformly on this non-conductor cylinder, and this is axis, everyone, and we want at this P point. Correct? All right. So this is Gaussian surface, everyone, and this P point is present on the surface, and distance between the axis and this P point is what? It is a small r. Correct? And the length of the cylinder is L here, and length of this solid non-conducting thick wire is infinite, everyone. It is going till infinite. Keep this thing in your mind. So case number 1, R is less than to the capital R, because point is present inside this non-conducting thick wire, that's why. Now write down here Gauss law, E dot ds equal to q in by epsilon naught. So what is the q in value, everyone? Q in is the charge present inside this closed cylinder, everyone, inside this closed surface. So what is the q in value? So q in is equal to what? It is the charge density. Charge density we are assuming here rho. So rho into volume of the cylinder. Correct? Which is, because this is cylinder, everyone, so volume of the cylinder can be written as what? Pi r square L. So this is the value of q in. Okay. So q in we got it. Now E and ds is parallel. So cos theta. Now I am writing a next step. E ds cos theta. And q in value we have rho pi r square L by epsilon naught. Correct? So here E and ds both are parallel. That's why theta is 0 and cos 0 is 1. And E is constant, put outside the integration. Then we have only ds. Correct. If we will add this small component present on the cylinder, then we will get surface area of the cylinder, which is 2 pi rl. Now pi r will get cancelled out. So what we will get here, E equal to, and L will get also cancelled out. So sigma r by 2 epsilon naught. Correct. This thing we will get finally, sigma r by 2 epsilon naught. And direction of position vector, and E is in same direction. So E is directly proportional to R. So we have linear relation, everyone, inside the non-conductor. And this is the case number 1. And keep this result in your mind, everyone. Rho R by 2 epsilon naught, electric field inside the non-conductor. Let's see its second case, everyone. Case number 2. Now this is the P point, and this P point is present outside the non-conductor, everyone. And this distance is small r. This distance is small r. And we want at this P point, so we need to consider here one Gaussian surface. So here we are assuming Gaussian cylinder, everyone. So the cylinder is present inside this Gaussian surface. Okay. Again, radius of the cylinder is capital R. Charge density is rho here. Length of this non-conductor is infinite, everyone. And condition is what now? R is greater than to capital R. Point is present outside this non-conductor. And the P point we want. So again we will write E dot ds equal to q in by epsilon naught. Correct? Now remove this dot product, then you will get cos theta. Cos 0 is 1. He is constant, put outside the integration. ds q in value is what, everyone? Charge present inside this cylinder. So q in is what, everyone? Whole charge is only present on the cylinder, everyone, and in the cylinder. So if I will multiply, and let's suppose length of this closed surface is what is the r. So rho and volume of the cylinder which is present inside this closed surface, that part only we will take, that volume only we will take here. So which is pi r square L divided by epsilon naught. Close integration ds is what? It is 2 pi r L. Now the next thing is what? Pi will get cancelled out, L will get cancelled out. Then finally what we have? Electric field is equal to rho r square by 2r epsilon naught. This thing we will get. So here electric field is inversely proportional to r, everyone. So here we have inverse relation, correct? Hyperbolic relation we have. Now we want to plot here graph. So let's see what type of graph we will get for this case. We want here electric field versus distance graph, correct? So inside the slender electric field, what we got it everyone? It is E is directly proportional to R, means we have linear relation, and outside we have hyperbolic relation. So graph should be look like this everyone. From center to surface, linear, and then hyperbolic. So this is the electric field versus distance graph. All right, note down everyone. Let's see next topic everyone. Electric field due to the large thin sheet, non-conductive sheet, and charge is present only on one side. So here what is happening, we have here large thin sheet or we have non-conductive sheet. In both cases we will use same result everyone. We will get same result for both the cases. If we have large thin sheet or we have non-conductive sheet and charge is present only on the one side. So when the charge is present on the sheet only on one side, then what is the electric field? This thing we want here. And for this both cases, we have same result, correct? Same derivation. Keep this thing in your mind, everyone. So here we have this closed surface, everyone, Gaussian surface. All right. And let's suppose this area is del S, everyone, cross section area of the cylinder, and sheet electric field lines due to the sheet. So this is electric field direction, everyone. Good thing is happening in both the direction. This is electric field due to this sheet. Correct? So if we will look this curved path, everyone. So what is happening? Field line is parallel to the curved path. So flux passing from the curved path is what? It is zero. Only flux is passing from the circular part, everyone. This field line is only crossing from this circular path, and here it is parallel. Correct. So we know that according to Gauss law, total flux can be written as Q in by epsilon naught. So what is the total flux here? It is E del S plus E del S equal to Q in by epsilon naught. Q in is what? It is the charge present inside the closed surface. So it is sigma del S. So Q in value is what, everyone? It is sigma del S, correct? 2E del S we will get if we will add this both. So we have 2E del S equal to sigma del S. Now the next thing is what here? Del S will get cancelled out. So we will get electric field is equal to sigma by, and it is Q in by epsilon naught. So here we have epsilon naught also, everyone. So we are getting finally sigma by 2 epsilon naught. This result we are getting. So we can see it here, sigma is constant, epsilon naught is constant, 2 is constant. Correct. So here this all things are constant, everyone, means electric field due to this thin sheet or due to non-conductive sheet we are getting, correct, constant. Means if I will plot a graph, electric field versus distance graph, so it will be look like this. So we are plotting electric field versus distance graph. So this type of constant graph we will get. So this is the graph, everyone. Note down. Let's see next topic, everyone. Conductive sheet. So now here we have conductive sheet, everyone, and in the previous case we have non-conductive sheet and charges present only on one side. So if we have a conductive sheet and we are giving Q charge on this conductive sheet, then what will happen, everyone? Then charge will distribute on both sides equally, correct? So on this side we have Q by 2 charge, and on this side we have Q by 2 charge, correct? And at this P point we want electric field, correct? So this is the closed surface, this is Gaussian surface, everyone. And charge is present on both sides of the sheet. Okay, and let's suppose this area is what it is, del S. And if we will see it electric field lines, here we have charge on both sides, positive, positive. So let's see it, electric field lines. This is electric field, everyone. Correct. So this is electric field. Now if you will think it, everyone, so electric field, correct, here if I will write total flux according to the Gauss law, so it is Q in by epsilon naught. Q in is what charge present inside this closed surface, correct? So if you will see it flux, so flux is only passing from the circular path. From the curved path, flux is not passing, it is zero, because field line is parallel to the curved path. This thing already we know that, correct? So total flux can be written as what it is passing from this curved path, from this circular path, and from this side circular path, correct? So here total flux, if I will write, so it is 2E del S, everyone. E del S, flux passing from this side, E del S is from this side, so it is 2E del S. And what is the Q in value, everyone? Q in is the charge present inside this closed cylinder, so it is 2 sigma del A divided by epsilon naught. So now here this 2 will get cancelled out, and this is del A, everyone, and del A we are considering del S here, and del S will also get cancelled out. So here finally we are getting E equal to sigma by epsilon naught. This is the electric field. So if charge is present only on one side, then electric field is what, sigma by 2 epsilon naught. And if the charge is present on both sides, or we have conductive sheet, then electric field is sigma by epsilon naught. So keep this thing in your mind, everyone. If we have a conductive sheet and charge is present on both sides, then sigma by epsilon naught. If we have, correct, non-conductive sheet, or we have large thin sheet and charge is only present on one side, then we have to write electric field is sigma by 2 epsilon naught. So this both cases are important, everyone. You have to keep this result in your mind, and you have to keep this thing in also, charge is present on one side or it is present on both sides, correct? Note down, everyone. Let's see this question, everyone. What is the net electric field at point A, B and C if two large oppositely charged plane thin sheet having the same magnitude of surface charge density sigma are placed parallel to each other? So here we have two sheets, everyone, and we want here what is the electric field at A, B and C point. This thing we want. So here we have four options and we want to see it which one is correct here. So at the A point we want, then we want at B point, and then we want at the C point. So first of all, we will put here test charge at the A point. So we know that test charge is always nature wise positive. So due to the first heat, electric field at A point in this direction, everyone, because force is acting correct toward the left, and on the test charge we have electric field due to the second seat. This is second seat, everyone, in this direction. So this is E1 and this is E2. If we will see magnitude of E1 and E2, everyone, then it should be same, because due to the seat and charge is present only on one side, so electric field can be written as sigma by 2 epsilon naught, correct? So, and we can see it here, due to the seat electric field is constant, it is not depending on the distance, correct? So E1 and E2 magnitude is same, direction is opposite. So definitely if we will add this both, then it is 0, because magnitude is same and direction is opposite, that's why. Now look at B point, everyone. Again put here test charge. So between the first seat and test charge we have repulsive force. So this is E1, everyone. And between the second and test charge we have attraction force. So this is E2. So at B point, net is what, everyone? E1 plus E2 is sigma by 2 epsilon naught plus sigma by 2 epsilon naught. Means it is sigma by epsilon naught. This is the electric field at the B point. Now look at C point, everyone. We are putting here test charge at the C point. Due to the first seat, electric field we have in this direction, and due to second seat we have in this direction, correct? Both are opposing. So we want at the C point. So electric field at the C point can be written as what? It is E1 minus E2. Due to the first seat we have electric field in this direction, everyone, and due to the second we have here. Both are equal and opposite, that's why EC is again 0. So we can see it here, EA is 0 and EC is 0, and EB equal to sigma by epsilon. Now check here option. So we are getting option number D, everyone. EA is 0, EC is 0, and EB equal to sigma by epsilon. So this is the answer for this question. So I hope this thing is clear, correct? Note down, everyone, and give me thumbs up.